All right, good morning, good afternoon, everybody. My name is Matthew Newstead. I am the Market Development Manager for Cannabis Environmental Food and Beverage here at SCIEX. And I'm super excited for the second part of our 5-part PFAS series, where in this particular session, we'll be speaking about quant, and nothing but the quant. There is a lot to learn, like we learned from session 1 on PFAS testing, a lot of gotchas and pro tips. And our speakers today will give you a brief summary of what was discussed in session 1, as well as speaking about the quant aspect in particular. I will tell you that the on-demand video of session 1, in case you missed it or want to revisit it, is available. So please go have a look at that. And I do need to make you aware that this session is being recorded. So we have 2 excellent speakers for you today. We have Dr. Craig Butt, and Craig, I lost my screen. There it is. Craig is a senior staff scientist for food and environment at SCIEX, and he comes to us with over 20 years of mass spectrometry experience that includes his PhD research, which happened to be on the fate of poly and perfluoroalkyl substances, or PFAS, in biological systems. At SCIEX, Craig's developed a variety of methods for screening pesticides in cannabis, non-target screening methods, working in high resolution and nominal mass systems, and has a wealth of knowledge to share with you on PFAS. And a quick plug for Craig, he has an excellent series called Fireside Chats, where he's talking with thought leaders in the PFAS community about all sorts of aspects around PFAS as it relates to environment and analysis. So a really great series. I encourage you to check it out if you want to kill a little bit of time one day. Our other speaker is Dr. Karl Oetjen, who is the Senior Technical Marketing Scientist for Food and Environment, Forensic, Clinical, and Cannabis Applications at SCIEX. That's a big mouthful. Before joining SCIEX, Karl did his PhD at Colorado School of Mines with Dr. Chris Higgins. His research there wasn't specifically focused on PFAS, but it was on environmental analysis and hydrologic science. And since doing that, his work did include aqueous film forming foams. My bad. I should have read the whole description before I rambled on. So aqueous film forming foams, a very prominent environmental source of PFAS that we'll be talking about, I'm sure, at some point in this series. And since joining SCIEX, Karl's worked with numerous labs creating and implementing a lot of regulated and unregulated, both quantitative and qualitative screening methods. So very excited to have both of these speakers here today.
Thank you, Matt. And yeah, thanks everyone for joining. Yeah, I really appreciate that you're here for the second session in our series. Just to kind of take you through the agenda for today, we'll start off, we'll be talking about the importance of chromatography, specifically kind of get into some of the recommended LC columns that we have found that work particularly well for PFAS. Of course, if you don't get the front end right, then you are limited in the sort of data quality you generate, and thus limited in your quant potential. So, before we discuss quant, we've got to talk about LC chromatography. We'll dive into talking about how to build good mass spec methods for targeted MRM analysis. This is your standard kind of analysis that might be done for a targeted list of compounds on a QTrap or triple quad. And then, once that data is generated, we'll talk about using software, specifically our SCIEX OS software, to really generate the data as quickly as possible, to get your final reports. We'll change gears a little bit and talk about using high-res instruments, specifically a QTOF, a time-of-flight instrument with a high-resolution MRM acquisition. And for those unfamiliar with this, we can use that technique and that instrument to improve our data specificity or compound specificity for better data quality. And then finally, Karl's going to finish up with a little session talking about suspect screening for quantitation. And this will actually nicely kind of feed into our next presentation or our next seminar in May. Okay, so this actually I grabbed from and modified slightly from the first session. And if this is, you imagine your kind of workflow from taking it straight from a sample prep through to your final data report. Last session kind of talked more on this, and now we're going to talk about, more specifically on the instrumental analysis, the mass spec method, and then the data processing. Okay, Matt's, kind of nicely mentioned part one, but I do want to emphasize, if you haven't had a chance, go back to the on-demand video, check it out. A lot of really good information in there, and a really good, background for what we're going to talk about today. And if you did miss it, the topic was, PFAS are everywhere, how to avoid them in your testing workflow. Karl and Sam spent a lot of time looking at sample prep. Here's just kind of a quick slide showing a typical solid phase extraction setup for a drinking water analysis. From there, some discussion was had in terms of controlling the contamination. PFAS are everywhere. A very big challenge in our analysis is removing that contamination. And one of the ways that our data does become compromised is with PFAS leaching off of the LC. And here, Karl spoke about using a delay column, a fairly common technique for separating that contamination that might come off of the fluorinated components in your LC. And then as well, again, these are just highlights. This is by no means an exhaustive summary of what was presented. And this, finally kind of touch on the fact of, Karl talking about controlling the contamination through carryover, right? So PFAS are relatively sticky compounds and have a kind of a bad habit of sticking around in our LC instrumentation. And there was a nice discussion on how to reduce some of the carryover issues. So again, this is by no means exhaustive, just really to highlight what was covered last time and to encourage you to go back and check out that on-demand session. All right, so we're going to start off talking about LC chromatography. And again, good LC chromatography is essential to get good data quality and therefore get good quant data. So, probably most people are familiar with the sorts of compounds that we analyze in PFAS. I think by some estimates, there's about 5,000 different PFAS compounds that are used in commerce. Realistically, on most people's monitoring lists, certainly for regulated monitoring lists, there is, a couple dozen. And most of the ones we look at are just listed here in terms of the classes. The better known ones are the perfluorinated carboxylates and sulfonates, and then some of these telomer sulfonates and sulfonamides. Moving into the newer, more novel compounds, these tend to be replacements for the older chemistry. These again are typically sulfonic and carboxylic acids, may have one or more ether functionality within that carbon fluorine backbone. And in some cases, we'll have a chlorine on them as well, usually in the terminal position. So, the common thing with these compounds, of course, is that they are acidic. They tend to have very low pKa's, which means they will be negatively charged during our analysis, which does mean that they are quite amenable for reverse phase LC conditions. And so when we think about choosing the column that we're going to use for our PFAS analysis, I'll show you on the next slide that the PFAS actually separate fairly well. You don't need UPLC, conditions, you don't need exotic stationary phases to get decent separation. But some of the things that you do need concerned about, and particularly this might relate to some of the regulated methods. So the PFBA and PFPEA, these are the C4 and C5 perfluorinated carboxylic acids. Those are typically more difficult to retain on a standard C18 column, which will often lead to maybe broad peaks or peaks that aren't well retained. So of course, one of our desires is to get good chromatography and good retention for those. Some of the regulated methods will require a measure of peak symmetry. So again, it will be important to have good chromatography for that. For a lot of labs, they are limited based on what kind of LC they might have in the lab. So some labs just don't have the capability to have a UPLC instrument. So one of the desired characteristics is to have a particle size larger than 2, so that you don't have a high pressure situation. And then of course, this is sort of more unique, not as many labs are running it, but if you are doing a high volume, so-called direct injection technique, then you do want that column to be amenable for that, and so that you that can hold that extra large volume, in some cases up to 1 mil. And then just some other concerns here, using a delay column that is similar or even a little bit more retentive to what you're using for your analytical column. And then of course, pH stability. So for some methods that require a base like ammonium hydroxide in the extract, of course, you want your columns to be stable at those very high pH conditions and not have that stationary phase degrade. So in terms of choices, and this is what we have found has been particularly useful for PFAS over the years. Our partners at Phenomenex make a really good column. It was a modified C18 particle called a Gemini. This has been found to, for large volume, show kind of no breakthrough even for a higher percentage of methanol. This here in a 97% methanol is more consistent with what the EPA 537 and 537.1 are using. And here, we found good peak shape. Remember what I said before, the C4 acid sometimes can have trouble with retention and thus peak shape. And again, we've got a good particle size so that you don't have the high pressures and stable. So that's kind of column 1, this Gemini column from Phenomenex. We've been using it for a long time in our applications. And here's just kind of showing a representative chromatography here. If we look at the earliest eluting compound, the C4 carboxylic acid, all the way up to the C18 carboxylic acid. And you can see good separation between the analytes. And as well, for something like PFAS, you can see separation between the branched and the linear isomers. So, very good column to use here. Another option that we've been using more and more in recent years, again, another Phenomenex column, is a PSC18. And so that is a positive surface charge column that does have kind of the C18 backbone. And of course, since most of the PFAS that we're looking at in our targeted methods are acidic, they have good retention to this positive surface charge. And then of course that C18 ligand will promote the retention with reverse phase mechanisms. And you can see here, I just have just sort of some cartoons to show available both in a fused core as well as a fully porous particle. So, great column, great stationary phase to use for the PFAS, and something that we're liking more and more. This just shows you a couple of examples of what the chromatography looks like. This is actually with a 3-micron particle PSC18. First, on the left-hand side, I just showed 2 example analytes, the C4 and the C5 carboxylic acid, showing good retention as well as good peak shape, nice symmetrical peaks. And then on the right-hand side, looking at 2 sulfonic acids, the C6 and C8 sulfonic acid. Again, we're getting good peak shape, but most importantly, good isomer separation. So we are able to separate the branch from the linear isomers, which can be important with several regulated methods. So again, that's just kind of touching on the importance of good chromatography and just some techniques that you can use in terms of your column choice. Because again, if your front end, is giving you poor results, then it's difficult, if not impossible, to get good quantitation. Okay, so I'm going to move on now, talk about targeted MRM acquisition. This would be the sort of analysis that you would be doing for with a triple quad or a Q-trap type of instrument. This talk is meant to be more broad, more educational rather than SCIEX specific. But for those that are running a SCIEX platform, just to highlight, if this was your SCIEX OS homepage, here we're looking at here these tiles, the MS method as well as the LC method for our method building. And first thing that you really need to be concerned about in terms of generating good data is your source and gas settings. And again, here I've mentioned the sources that we have with SCIEX, the Turbo V, the Ion Drive, and the OptiFlow Pro. But really, that is to say that all of these sources and that you encounter will have different personalities. We'll say that in terms of their heating efficiency and their gas flows. And so you need to be sensitive to that when you are transferring methods over, either from something that's in the literature or something from your colleagues, because really this is where you kind of start your process, because you want the best ionization to get you the best data quality, but also if the conditions tend to be too harsh, then you may have in-source degradation or degradation of your analytes. And PFAS are known as being these forever chemicals, but it is important to note that if conditions are too harsh, then some of them will start to degrade. And so specifically, the perfluorinated carboxylic acids, right, that carboxylic acid group will fall off fairly easily in a source under harsher conditions. So specifically, PFOA or something HFPODA, which most people would know as Gen X. And so because of that, these compounds, the perfluorinated carboxylic acids or the perfluorinated ether carboxylic acids, they tend to prefer softer conditions. And so what do I mean by softer conditions? I mean things like the source temperature tends to prefer to be somewhat lower, as well as the ion spray and sometimes even the gases. In contrast, compounds like PFAS or perfluorohexane sulfonic acid, those sulfonic acids are more stable. And they generally prefer higher temperatures and ion spray voltage to get you better sensitivity. And so, some of you may have discovered this in your lab when you're doing your optimization. But, maybe what's coming to mind is, well, it seems like we've got 2 polarized groups of compounds here. What do we do? And so ultimately you have to kind of decide if you want to bias your sensitivity to one class or the other, or choose something more in the middle to give you kind of a happy medium to get overall good sensitivity for all the classes that you're interested in. Graphically, I've shown this here on this page. I just want to take you through it before I look at the trends. Here I have 3 sources from our SCIEX instruments. The OptiFlow Pro, which is on our most sensitive triple quad, the 7500, the Ion Drive, which is on the 6500 plus, and then the Turbo V, which is on the 35, 45, and 5500 plus. And so those are kind of three different sources. And then here, the more kind of rainbow colored are the carboxylic acids of various chain lengths. And then down below are the sulfonic acids, here in kind of more the reddish colors, reddish hues, and again, various chain lengths. And so if you look at just here as an example, source temperature, first thing to note is that here for our OptiFlow Pro source, really, the carboxylic acids, once they start to get too high of temperature, start to degrade, and you lose sensitivity. And sorry, I should say though, here the y-axis is just a measure of signal intensity, normalized to 100%. So carboxylic acids start to degrade when it gets too hot. And whereas the sulfonic acids actually don't mind it and prefer it for a little bit of sensitivity. You can see here that the Ion Drive source, not quite as sensitive, but still shows that peak at the lower source temperature, whereas the Turbo V, which is an older source, not quite as efficient, not quite kind of as hot, and it doesn't show that maximum until slightly higher temperature. So really all of this is to demonstrate if you are trying to get the most sensitivity out of your method, it is important to know the personality of the specific source that you're using on your instrument. And it can be dangerous, meaning that it may not be completely applicable if you're just grabbing these conditions that were achieved on a different instrument model or even a different vendor model. And then finally, just to know that the two classes of compounds do behave differently just based on their inherent stability within the ion source. Okay. So again, in terms of building your method, right, this is fairly straightforward. Assume most people would do it. Here we've got our components that we're putting in, our precursor, and then our fragments, and then setting our optimized collision energy and collision exit potential. This is actually on a 7500 where a declustering potential is not user modified. But if you had another instrument, then a declustering potential would need to be optimized and put in your table. One thing here to note is cycle time, okay? And so this can sometimes be, let's say, underappreciated in terms of good data quality. Here I've set a cycle time of 600 milliseconds or 0.6 seconds. And why this is important, because depending on the concurrency, so by concurrency, I mean the number of transitions that I'm monitoring at the same time, then will depend on how many data points there are across the peak. And in our case, in the way that this is set up in the software, to determine our concurrency, we have a target, our known retention time, and then a retention time tolerance. So you see here where it says apply, scan, schedule. This is really saying that only during these windows of retention times are we going to be monitoring that transition. And so if you haven't used this technique, right, this is very essential for large panels of compounds like PFAS, so that you're really only monitoring those transitions during the times in which those analytes come out. And that will help maximize and really optimize the number of data points across the peak to give you the best data quality. So just the way that this is set up with this software, we have an automatic calculation of the dwell time, the amount of time it's spending looking for that compound when it's turned on. But certainly other software will do it slightly differently. The key, really, what I want to drive home with this is that target cycle time is very important. to get sufficient numbers of data points across the peak. Okay, so where do we get that? Oh, sorry, that's going to be in the next slide. Before I go too far with that, what I do want to talk about is the collision energy trends. And so one thing is that, again, our major classes of PFAS do have their own characteristics, their own personalities. As I mentioned before, the sulfonic acids are more stable. And typically the only kind of fragments that we see are breaking of the sulfonate bonds to form an SO3 fragment, which is a 80 Dalton fragment, or the FSO3, which is the 99 fragment. I'd be very cautious, and this is something we're going to get into in a later series, or sorry, later presentation. But that 80 fragment, the SO3 fragment, has been shown to have some biological interferences with both PFAS and perfluorinated hexane sulfonic acid. So generally, for best data quality, particularly for those biological extracts, you do want to use the 99. Trends in terms of the perfluorinated carboxylic acids or your ether carboxylic acids. As I mentioned, that CO2 group, the carboxylic acid functional group, is very labile. So typically, one of the major fragments you see will be the loss of the 44 Dalton, the CO2. And then some form of a smaller perfluorinated carbon chain. Now, what I should say as well is just by nature of the thermodynamics, very, very short chain perfluorinated carboxylic acids are not stable, which is why for some of the short chain PFCAs, you only see the one stable fragment, the loss of the CO2. This can be confusing when you're using methods that use two transitions. But for these short chain guys, they're next to impossible, I would say, to see any other stable fragments. All right, so getting back into my points across the peak, kind of slight little diversion there. Here, if we get back to our early eluting PFCAs, the C4 and C5 acid, here what I've done is I've actually looked at the number of data points that are across the peak. And you can see we've got about 11 to 12, depending on how you count exactly where the baseline starts and ends. And what we have shown is that you do want 10 to 12 data points across the peak for good precision and accuracy. If you have a situation where you have a pyramid of really, one data point at the baseline, one for a peak, and then a third one at the end of the peak, you're just not going to get good data reproducibility. And so that is one thing when building methods and you're having kind of imprecision issues, that's kind of a first one to look at. And really, frankly, anything more than 12 data points across the peak, then it becomes a little excessive. And so where my 600 milliseconds cycle time comes from, or targeted cycle time, is really the number of points across the peak that I want, 10 to 12, by the peak width here. And so that's how we come up with that number. Okay, so now we're going to go from the method building and start to look at the actual data processing. Again, if you were using a SCIEX software, this is in the analytics tile. And if those are not familiar, this is similar to what you may be using with a multi-quant software, but in fact is more powerful, as we'll show you, and easier to use. All right, so of course, not all methods do use internal standards, but something that if you have that flexibility to use, then certainly it is encouraged. For some methods, it is required. But certainly using mass labeled internal standards will improve your precision and your accuracy. You can see here what we've done is, there is a large suite of BAS labeled standards available now on the market. We typically use our standards from Wellington Labs, and they do have custom-made standards for some of the different regulated methods. And so here is kind of a grouping here. First thing is, you can see in our software, we're designating certain compounds as internal standards. So that's your first step. And then here, from a drop-down menu, we are able to assign those internal standards to the specific compounds. And just kind of, if you're following along with your software in your lab, this is in the components section. This is information that is grabbed actually from my acquisition method from the data file. So it doesn't require any additional altering for the precursor, fragment, and retention time. It's just really here where I'm setting up that internal standard and designating it. And so depending on what sort of method you're using, you'll have some that are spiked in before your extraction, and then sometimes also some that are spiked in at the very end, before your analysis. Okay. The other thing too, typically that's done in these methods is for good QA/QC is looking at ion ratios. So not every method will monitor more than 2 transitions. This is assuming that you are monitoring more than 1 transition. And what you're doing, you can see here, right? I have 1 transition and then a second transition for PFBS. And what we're doing is we're looking at the ratio of those 2 transitions. And so from our standards, we know what that ratio should be. And so when we do have a positive hit in our sample, we want to be sure that that ratio is consistent with what we expect. And if it's not consistent, then we know that perhaps that we don't have the right compounds. But to do this, it's fairly simple. You kind of need to tell the software that they belong to the same compounds before it can do those calculations. So if we look at that, again, if you are kind of following along with SCIEX in your lab, under the flagging rules, there's an option to do this ion ratio acceptance. And here we can calculate a constant tolerance, meaning that what we see as acceptable will be consistent for all of the analytes. And there's another option for variable if you want to change it depending on the magnitude of the ion ratio. But again, that's something that can be done right within the software to kind of speed up your QA/QC monitoring. Okay, calibration curve settings. This again is in our processing method workflow. This would be the next tab down in integration. You'll see here we can set the type of regression. In this case, it's not showing the whole thing, but this is linear through 0. So in some methods, it is you are required, for example, some of the EPA methods, you are required to force your regression through 0 rather than having a y-intercept. So this is something that you would change straight up, as well as here's some of the weighting type. Now, this can be adjusted later on during your results table, but here's how you can do it in the processing method to get that kind of flexibility. Okay, so I have a special section for this because I know this is one that kind of tends to lead to a lot of frustration when doing the PFAS analysis. And that is the integration parameters when looking at some of the PFAS analytes that have both branched and linear isomers. So what do we mean by that? Compounds that were produced by electrochemical fluorination, and this was primarily for some of the 3M compounds that were produced, some of the sulfonic acids, sulfonamide compounds. This electrochemical fluorination process was very violent and produced both linear and branched isomers. The other method that was used to make PFAS called telomerization actually only produced linear isomers. And why that's important is that on most chromatography methods, you will see both this linear isomer as well as some preceding peaks that are branched isomers. Now, you'll notice this one here kind of looks like it's a bit of a peak splitting, and that's because there are lots of different branched isomers, and this is kind of one kind of big hump of some of them, and you can see even a smaller preceding peak here. So, for some of the sulfonic and sulfonamide compounds, if you do see this in your method, this is not poor chromatography. This is actually good chromatography, right? It says that you're getting that separation of branched and linear. Why that's also important too in terms of your PFAS analysis is that many of the regulated methods require you to in fact show that you can separate them. You do need to kind of show an auditor that you can separate them. However, they generally require that you report a total, in this case, PFAS number. This is challenging, right? This is challenging because typically we would only integrate one linear Gaussian peak. All right, so I kind of alluded to it on the last slide, but typically, right, a software is built to ignore these kind of peaks here because it thinks it's noise, and really give you a nice integration of a single Gaussian peak. So in fact, typically this is what you would like. And here I've got just some integration settings in the SCIEX OS analytics. However, as I kind of mentioned on the last slide, this is typically not what is needed or required. We need to integrate everything together to get a total PFAS number. Now, how do we do that, right? We could do manual integration, but of course, doing manual integration for a large number of samples is both time consuming, but there is inherent variability. So we can actually change some of the integration settings so that we now integrate everything together. And these are just some of the parameters specifically that we set. And what it does is it really kind of tricks the algorithm and says, no, grab more of that apparent noise, and we can get it all together. The importance with that is that now we have a more automated procedure, which is more consistent, so saves time, and you have better data quality and more precise reproducible data. Okay, so now I'm going to switch gears for the last little bit of my section and talk about using a high resolution MRM method with a QTOF instrument. Yeah, these are the sort of QTOF instruments, high resolution instruments. This is one that we have at SCIEX called a X500. Very strong, powerful instrument, very sensitive. And here, instead of having a third quadrupole, we have a time of flight chamber. Another one, fairly recently introduced now, is kind of the next step up, the Xenotrap 7600, similar to the X500 in many ways, but more sensitive through something known as a Xenotrap, and also has a different form of fragmentation that you can engage as well, in addition to CID, or collision-induced dissociation. So with MRHR, again, very similar in terms of setting and optimized declustering and collision energy. But the trick is that you're not actually going to be monitoring a single fragment, but you're getting a scan of the fragments. And these scans are obtained in very high resolution and very high accuracy. So what does that mean? Is that, setting up the methods here, just kind of zoom in again, we're optimizing those parameters to give us the most sensitivity as possible. Okay. But what does it mean to monitor something in high resolution? Well, getting back to my PFAS, right? So here's my normal PFAS coming out of the LC. I've got my branched hump and my linear hump. But when we look at the fragment ion scan under it, I want you to pay attention here to my x-axis. So if you'll notice here that we are now seeing that fragment mass peak very, very fine, or a very high resolution. And to give you an example, really kind of zoom in on it here, this width of the box is 0.02 Daltons, okay? So what it means is that we know the mass of this fragment to a very precise number, to kind of the third or fourth decimal place. And so now, instead of saying that this fragment ion is, here my FSO3, 99, really what we need to do is we need to say we know it at 98.9558, because you can see through my x-axis here, we can clearly distinguish that from something at, let's say, 98.98, okay? So the importance of this is that it gives you better selectivity. As an example here, this is the width here in these red bars of what you would see on a triple quad, right? Whereas we know the precision of that mass very, very finely. And the importance is that in terms of building your methods, is that now you do need to pay attention to the decimal places, and you need to know, or you need to put in the accuracy of that fragment very precisely. Okay, and so the importance of that for your data quality, I think this is the last slide before I pass off to Karl, is that because you know that fragment mass so well, you can distinguish it between things in the matrix background. So for things like sediment or river water for this Gen X compound, you can see we have very, very low background because we're really extracting that precisely rather than grabbing a whole bunch of matrix in our analysis when we're doing that monitoring. So with that, I'm going to pass it over to Karl, who will talk about using suspect screening.
Thanks, Craig. So Craig was nice enough to go ahead and save my favorite part for me. So that was great. So we're going to talk a little bit about suspect screening. So when we kind of cover this topic, it's really meant to just be an introduction to the idea and kind of a little bit of a teaser for our next session, which is going to really focus on high resolution mass spectrometry. So we're talking about targeted analysis, right? Craig was talking about quant. It's all about quant. So that would fall into our targeted analysis bucket. So targeted analysis would be kind of answering the question, what compounds are here? Do I see PFAS? Do I see PFOA? Can I quantify them? That's really what you're doing with the kind of workflow that Craig presented. For suspect screening, our question's a little bit different though. Our question is going to be focused on what compounds are present in my sample of this defined list. And what's unique about that is that list could vary. It could be that those compounds, you don't have standards for. In fact, many times those standards don't exist. Or it could be that maybe you do have standards, but you don't include them in your sort of daily workflow. So this is typically a little bit more complex workflow. So to go ahead and do that, we're going to apply certain different experiments. So let's go ahead and click over. There we go. So for a high resolution system, we're going to be talking about maybe MRHR max, kind of like what Craig was discussing, an acquisition type called swath, which we'll go into extreme detail in the next session, or some other type of information dependent acquisition approach. If we were using a QTrap rather, we'd really be relying on an MRM EPI experiment. But regardless, we're doing the same thing, right? We're trying to answer that question: are these compounds present in my sample from this defined list? So just to kind of rehash and bring back what Craig was speaking about when we were doing traditional MRM analysis, right? I like to use these little diagrams because I think they help me. But for a triple quadrupole, right, we're using our first quadrupole to really filter out an ion. So in this case, we're going to focus in on that 215. So we've got that 215 ion. Our first quadrupole is going to filter out the other ions and allow that ion to travel into our collision cell. In the collision cell, that's where fragmentation is going to take place. So our ion's going to fragment. And then on a triple quad, we're going to use that Q3 to really focus in on a specific ion. So in this case, let's say that 185. So our third quadrupole is going to filter out all those other things, or all those other fragments rather. And that 185 is going to make its way to our detector. And we're going to quantify off that. So how does that differ from, say, QTOF? So QTOF, right? Quadrupole, time of flight. So the first thing we're going to do is the exact same thing we were doing before, right? We're going to take that 215. How we select that 215 can kind of depend. Craig showed a great example of using an MRM experiment to sort of go ahead and choose that ion. But in the next session, we're going to talk about some non-target approaches to selecting that precursor ion. But here, regardless of which way we do it, the process is the same. So we've got our 215 ion. Our first quadrupole is going to filter out all those other ions just like before. In Q2, fragmentation would take place. So we're going to have some fragmentation. And then we could either focus in on that 185, or we could go ahead and look at all our ions. But regardless, all our ions are entering our time of flight and they're being separated. So when I describe time of flight to someone, I usually describe it as a really good tape measure and a really good stopwatch. So it's obviously a super oversimplification, but in general, that's kind of true, right? We know how far those ions have to travel, and we know how long it takes them to get there. And sort of the basic of that would be that, hey, the bigger thing's going to take longer. So that's exactly what we're doing. So we're going to utilize that to do some suspect screening. So the first part of doing any suspect screening analysis is to create a suspect list. So here we have a populated list. We have all the ions I want to look for. Maybe I have standards for some of these, maybe others I don't. Maybe a colleague told me, hey, could you keep an eye out for this unique PFAS compound? I can go ahead and add it to my list. The only criteria is that I need a mass and I need a formula. So as long as I have a mass or formula, I'm good to go. I can go ahead and search my data for that. So here would be an example of that. So here we have a compound that I do have a standard for. So this is kind of like what Craig was showing before. I can match it to my retention time, right? Because I ran the standard on my instrument, so I know it's retention time. I can then match the precursor and fragment mass. So that would be my second piece of sort of confidence that this is indeed what I'm looking at. I know that formula, so I have this really nice isotope pattern. And then arguably, most importantly, we have this fragmentation information. So unlike a triple quad where we're just looking at a transition from a parent to a daughter ion or a precursor to a fragment, here we're talking about, here are all the fragments. We're looking at essentially that compound's fingerprint. So yay, I'm happy. This is a good hit for this compound. But what if I didn't have a standard? So let's go ahead and say I wanted to screen a library, for example. Well, one of the things I could do is populate a list from that library. So here is just an example of the SCIEX HFFF library. So this is a library that myself and a colleague of mine went ahead and made some years ago. And one of the things about this library is a lot of these compounds there aren't standards for. So you can actually go ahead and purchase a standard and run it on your instrument. You're going to have to really rely on that fragmentation information, that parent mass or fragment mass, depending on how you're doing your analyses. So your mass accuracy, and then that isotopic information to get a nice confirmed, this is the compound I'm looking for. So what would that look like? So here I have an example of that. Obviously, we could purchase a standard for PFBA. It's in most EPA methods. Well, it's in 533 and 1633. So we could purchase it, but let's pretend in this experiment, we didn't have the standard available. We didn't expect this compound, perhaps, but we included it in our suspect list. So we wouldn't need to rely on things like retention time because, well, we don't have retention time. So we have our mass accuracy, which in this case is very good. 0.3 ppm is great. Really anything sub 5 is kind of the gold star. We have some isotopic information, but then most importantly, we sort of have this fragmentation information that we can match to our library. So on the right-hand side, we have our fragmentation. Above, we have the data we actually collected. And down below, we have the data in our library. So we see we get this nice match. And we're really matching to that blue spectrum. So that pink spectrum, we're going to talk about in the next session. But what I really want you to kind of gather from this is the blue represents the deconvoluted and represents really what is related to that peak or that compound of interest. So that's great. We have something in the library that we can match to. So that's a good scenario, but it's not the only scenario that we're going to come across, right? There's a lot of gray space when we talk about suspect screening. So in this example, we have a match. We have a really nice match for this hit in our suspect list, but we don't have any fragmentation information in a library. So if it's not present in a library, how can we be confident that this is truly our compound? Right now, we only have mass accuracy, right? Which is important, but it's not the only thing. So we're going to go into detail quite a bit in our next session about how to do some of the structural elucidation and confirmation searching when you're doing suspect analysis. But just as a little bit of a teaser, in this case, we use diagnostic ions to get at whether or not this is an appropriate match. So we've got a nice mass accuracy, great. Our formula makes sense. Our isotopic information makes sense. We don't have any fragmentation, but we know some of these ions are pretty diagnostic of sulfonated PFAS compounds. So we have that SO3 or that AD fragment, which we can say, hey, yeah, I'm pretty confident this is the compound I'm looking at. So with that, I want to go ahead and encourage you to attend our next session. It's really going to focus on high resolution mass spectrometry, and based on the polling question that you answered in the first session or the first section of this, it's going to really help guide that session. So I'm really excited for it. It's my personal favorite topic. So I think it's going to be a really good session. And with that, I'd like to open it up for any questions.